Hello there. In this video, I really quickly want to cover a kind of niche technique that can be used to solve for not just Quartic. I'm going over Quartic in this video, but I've seen it used on Quintix. I'm sure it could be used more. But again, it's kind of a niche example. It doesn't always work, and it's kind of something that, like, once you head down the rabbit hole, hopefully it does work. Otherwise, it's a gigantic waste of time. So the idea will be to factor this polynomial out. So I'm going to let this equal a polynomial of x squared plus ax plus b times another polynomial x squared plus cx plus d. And what I'm effectively going to do is I'm going to solve for a, b, c, and d. Now notice, if I were to FOIL this out, x squared times x squared is x to the fourth. So this is one time when you might want to use this, is when your lead coefficient is 1, then creating this factorization is nicer because you don't have to find for extra constraints, E and F, maybe, that would be lead coefficients of these individual polynomials. The other way we can recognize when to do this is, notice we don't have a cubic term. Anytime you're missing terms, it kind of works out great. I shouldn't say it works out great. That's not a way to describe it. It might work out a little bit better than expected. Okay, so what I'm going to go ahead and do now is I'm going to go ahead and use my area model method for multiplying these two polynomials together. I'll do that really quickly. Okay, so the idea of this method is that I've multiplied out this factorization that maybe exists, maybe it doesn't. Maybe it exists with rational numbers, maybe it exists with integers. That would be the best case scenario. Maybe it exists with irrational numbers, and like square root of 2, square root of 3, that we can write in their exact forms. But the point is, when we multiply this out, we have matching coefficients. So notice x to the fourth matches to x to the fourth. Now, x cubed. The coefficient for this expanded version is a plus c, but what does a plus c equal on the original Quartic? And that's 0 because there was no x cubed term. Now we have the x squared coefficient, that's b plus ac plus d. That would equal the -5 here. We've got the ad plus bc. That would equal the 50 here. And finally, we got the BD. Try and squeeze that in there. That equals the -156. Okay, so let me go ahead, cut really quickly, and we'll start off on a clean page. Okay, so we have a system of 4 equations, and we have 4 variables. This works out nicely because we might be able to solve this. So the idea will be to whittle down the variables. Well, this is where having no x cubed term comes in handy, because I can write this as c is equal to -a. You could also write a equals -c. And what I'm going to do is I'm going to take that and I'm going to sub it in wherever I see c. So I see it there. I see it there. All right. Enough goofing off. All right. So we got b plus a times -a would be minus a squared. So let's actually fix that. Minus a squared plus d is equal to -5. And I've got AD minus B times A. So I'll write it as AB equals 50. And then BD equals -156 does not change. Okay. Now let's go ahead and try and figure out another variable to solve for. Let's go ahead and solve for B on this one. So B is equal to, well, we'll add the a squared to the other side, so a squared, and we'll subtract the d, and then we just have, or not equals -5, -5. And we will put this b here, we will sub it in here and here. So, okay, we're going to take this becomes AD minus A times A squared minus D minus 5 equals 50. Okay. Ooh, I think I'm seeing something from that I like. No, maybe not. Okay, and then here we've got D times, we've got A squared minus D minus 5 is equal to negative 156. Okay, so let me do another cut, and we'll start with a fresh screen again. Okay, so as you can see, the attempt to try and whittle it down and solve for variables, I mean, you could probably try and solve this, and you could probably go to Wolfram Alpha and ask for integer solutions or just solutions in general. Probably should start with integer solutions because there's infinitely many irrational solutions, I'm sure, to this. So, but I don't know. Like this is where what kind of dead end this can lead you to. So what I'm going to do instead, let's go ahead and go back. I'm going to clear the annotations here, and then I'm going to go ahead and just do a real quick erase here. And what I'm going to do is I'm going to try a more guess and check approach. And this is what I mean by when you try this approach, you need to be sure that you can go somewhere with it, because otherwise you're going to go down a dead end, and I especially have problems giving up. So what I'm going to focus on is I'm going to focus on this equation right here, because I got two numbers that multiply to give me negative 156. So let's focus on factors of 156. That'd be 1. So what this should do, we know this equation is going to check out. So let's go ahead, let's try, say, 12 and 13. Let's go ahead and plug it into this one right here. So we've got, oh yeah, and then let's not forget pluses and minuses. So let's start, say, with plus 12 and minus 13 as a sort of arbitrary guess. So we got 12 plus AC minus 13 equals negative 5. Okay, so 12 minus 13 is negative 1. Then we'll add 1 to other side. We get negative 4. Pardon me. So right now what we've got is AC is equal to negative 4 and A plus C is equal to 0. Really quickly, let's go ahead and plug it in here as well. So we got 12. We got 12 times, or no, sorry. Pause, rewind, let's run it back. Okay, negative 13a plus 12c is equal to 50. That doesn't really help us. By the way, I'm assuming this is B and this is D. Okay. Well, I mean, this could work, but let's really quickly focus on, I have a product here and a sum here. That looks a lot like diamond math. So I'm going to go ahead and set up a diamond math, negative 4 up top, the sum down in the bottom, and that is actually negative 2 and positive 2. So I have potential values for A is equal to negative 2 and C is equal to positive 2. Or the other way around, we don't know. So let's really quickly, I'm going to go ahead and check this. So negative 2 plus 2 is equal to 0. That checks. Plugging that into here, which was left over from here, that would work. So that checks. Well, negative 13 times negative 2 plus 12 times 2 is equal to 50. We get 26 plus 24 is equal to 50. And we have our answer. Great. Wasn't that lucky? It actually wasn't lucky. I knew the answer the entire time. Yeah, this is a problem I reverse engineered to be able to show this method. I wanted it to be as complicated as possible because I kind of wanted to show my frustrations when I explored this method. I went down many dead ends before I realized if I want to show this in a video, I have to reverse engineer the problem. So yes, I did know that this was our answer. Specifically, the way we wrote it at the beginning is negative 2 has to pair with 12 and 2 has to pair with negative 13. If we show that any different, we get a negative 26 here and we get a negative 24 here, and that gives us negative 50. So this final equation wouldn't check out. And if we tried any one of these, they wouldn't check out. Now, if any of those didn't happen to happen, then you're stuck. You might have to resort to using rational zero test or Newton's method or something. So let's go ahead and write these out. This would be, the final results were x squared minus 2x plus 12 times x squared plus 2x minus 13 equals 0. Now this is great because we've got it down to quadratics. We can use the quadratic formula. We'll go ahead and do that now. As our final two solutions. So all in all, what do we take away from this? Well, I'm not an expert in this method, so I can't really give the best advice on how to and when to use this approach. It's kind of a crapshoot. Okay, you have to be wary that it exists. Use it as a tool. But don't get married to it. I thought maybe it was like the end-all be-all, like this is a way we can solve quartics and maybe even quintics more easily, until I remembered quintics are not solvable. At least one method can't be used to solve it. Otherwise, we would have a quintic formula. So what did I discover? When I went through this and explored this, I tried it with quadratics. I really did. And then I kind of realized that's kind of stupid because you have so many methods already to solve quartics. I tried cubics. I never really gotten anywhere with that. My advice would be use it for quartics only. Approach with caution with quintics. I personally wouldn't try it with hexics. 6-degree polynomials, just because those, this was just a quartic. It was a nightmare. Plus, only try it if you're missing some terms. The more terms you're missing within the polynomial, the better. Obviously with a quartic, if you're missing enough terms, then you don't need to rely on it. So maybe if we were missing one more, like the quadratic term. So let me write this out. This term was missing the cubic. Okay. Oh. This term was missing the cubic. Okay, try it then. If we're missing the linear term, then we have a biquadratic, and we can use a modified version of quadratic formula or factoring to go from there. Okay. If we're missing the constant term, then we have a lead coefficient of x. Sorry, not a lead coefficient, a greatest common factor of x. We can take out of the 4 terms or remaining terms, And then all we're solving is a cubic. So that's great. So if you're missing the cubic and then maybe the quadratic term, then you can go ahead and give this a try. I thought it was worth showing just simply because it's another tool when solving polynomials. It's not immensely reliable, but you can never have too many tools in your tool belt. Anyway, I've extended this conclusion enough already. I'm rambling, so thank you for watching.